speakers. One of them's returning, one of them's brand new. We have a little tradition for brand new speakers, so before we get started, we're going to do a shot.
Sure.
Break a leg, guys.
Hello. So good afternoon, everyone. Today we will present a topic about kernel security. One byte and all your dreams will come true, analyzing and attacking Apple kernel drivers. So this is Bai Xiaolong. My name is Zheng Mi. You can call me Spark. We are PhDs and work for Alibaba. So here is the agenda. First, we briefly introduce what is kernel driver. Then we talk about new vulnerabilities in Apple drivers. After that, we will talk about obstacles in analyzing Apple drivers, and then introduce a new tool called RIC for analyzing and fuzzing kernel drivers. So let's start. First thing you should know is every driver in kernel in XNU is a kernel extension. They share a same space with the kernel. On Mac OS, the drivers locate in the system library extensions. On iOS, drivers are integrated with kernel in the kernel cache. Kernel drivers provide user client, which are kernel objects for drivers to provide service to programs in user space. Also, user client is the interface between user space, applications, and devices. In order to provide services, user clients need to implement several callback methods, like external method, client memory for type, register notification port, client close, and so on. The most important callback method is the external method, which provides the methods to user space program. The selector is used to select method in user client. Arguments are passed to the selected method. Dispatch is a struct representing the method to be called. The target is the target user client for the method to be called on. Reference is the result, which is sent back to the user space. Despite the strict sandbox restriction, some user clients are still be accessible to sandbox apps on iOS. For example, IO-HID lib user client and IO service root user client. So now we will share some vulnerabilities we found in Apple drivers. The first thing you should know is the driver are good targets for exploiting the kernel because they share the same space with the kernel and they have the same kernel privileges. So some drivers are programmed by third-party vendors, not the kernel developers. So the code quality is not guaranteed. So a lot of drivers are frequently exploited in attacks against the kernel, including the jailbreak. A lot of vulnerabilities are used in jailbreak. For example, iOS 11 used IO service root. Pangu 9 used in their first version they used IO-HID family, and the second version they used the IO buffer frame, IO mobile buffer frame buffer. This is the first vulnerability. It is an information link in IO fireware family. It is caused by an initialized kernel stack variable, which is out channel handle in the ISO channel alloc case. As you can see in the IOCH channel create, the out channel handle is passed into the add object function. In this function, you can see the out handle should be set with the index of new added object. But when the new capacity reaches FFFE, new object will not be added, and out handle will not be set. Recall the allocation case in external method. Out handle is initialized variable and returned to user space. So that is an information link. You can use this information to help you to get the kernel slide and then defeat KASLR. The second bug is a user after free vulnerability in the I/O accelerator family 2. It has a method called sTransactionEnd. In this method, the user client will call transaction end in I/O accelerator display pipe 2. Note that all user clients share a same pipe 2 instance. Pipe 2 contains a linked list for transactions, and pipe 2 will traverse the linked list to find a transaction, and then call the set transaction arguments for the found transaction. However, in the transaction argument, transaction arguments function, pipe user client 2 is a member of transaction 2, and the function will call the return method of the user client. But the pipe user client can be released by calling I/O service close for the from user space, which we'll call the user after free. So here is the steps for exploit this bug. Firstly, we create two pipe user client. Then we add a transaction for the first user client. And then we release user client. After that, we end the transaction from the second user client. It will trigger the user after free. But this bug is fixed because now the pipe user clients don't share a same pipe. So how to exploit a user after free bug in the kernel? Here is the basic flow. Firstly, we construct rope chains and then trigger the release. After that, we use a fake object with fake vtable to occupy the empty slot. Last but not least, we trigger the user after free by invoking the method of old object. The heap spray technique we used in this vulnerability is OS uncentralized XML. You can invoke it by setting properties of a device. Note that the sprayed data can be read and the head of sprayed data is controllable. So this is the rope chain for the privilege escalation. Firstly, we use a stack pivot to control the stack, and then get the pointer to the struct proc of current process. Then we get the uCredit from proc and set CRUID, CRRUID, and CRSVUID to 0. After that, we will use thread exception to exit the kernel mode and return to user mode. Then we can execute the system bash to get a shell with root privilege. The stack pivot we used in this rope chain is the following gadgets are used in the stack pivot. At the beginning, we use REX to control RCX. Then we use RCX to control ISP, which is the stack pointer. So here is the layout of gadgets in a rope chain. Note that REX is controlled by us. By using these vulnerabilities, we got a privilege escalation on Mac OS 10.11 10.13.2 and 10.13.3. So here is a demo on 10.13.3. As you can see, we got a root shell in this macOS. So Xiaolong will talk more about drivers analyzing and fuzzing.
Okay. Thanks, Scott. And next, we are going to show how we found those vulnerabilities. And Apple drivers are mostly closed-sourced. In order to find vulnerabilities, we need to do some reverse engineering. But it is not that easy. Let's first have a look at the decompiled code of driver binaries in IDEA Pro. In the decompiled code of macOS driver, you can see that the function names are kept, but there are many problems, such as wrong parameter inference, lost variable types, and unknown virtual function calls. As for iOS kernel drivers, the situation is even worse. We have no idea of what this decompiled code represents. It's a mess. In fact, in order to find some vulnerabilities or do some resolution, we want the decompiled code to be just like the source code, just like the figure suggests. So we propose a new tool to analyze drivers in macOS and iOS. This tool is called Ryuk, which is a statistical analysis tool for making Apple drivers decompiled code more like source code. It is implemented as an IDEA Pro Python script. The name Ryuk stands for a character in the comic series, Death Note, who loves eating apple. So Ryuk has several features as below. It can identify name, size, and vtables for classes. It can recover function names, resolve variable types, extend cross-reference, extend UI support, and construct all call graphs. So firstly, Ryuk identifies name and size for classes. We identify this information from some specific initialization function. As the figure shows, a sample initialization function looks like this. You can see that this code indicates some information of the class, for example, its name and its size. With these identified class name and size, we can create structures in IDEA Pro to represent these classes. Besides, Ryuk can also identify vtables for classes. You should know that in C++, if a class has any virtual function, it always has a structure called vtable to organize its virtual functions, just like the figure suggests. We identify classes vtables with a hint, and that is, ahead of a class vtable, there is always a pointer pointing to the class meta class object. This is a special object. And recall that in the special initialization function, this function also shows where the meta class object is. So with about hint, we can use the meta class object address to find the class vtable. And after that, we can create structures in IDEA Pro to represent these vtables, and send the first member of class structures to a pointer to their vtables. The next feature of Ryuk is recovering function names. As we can see, iOS drivers are lost of symbols. Functions in iOS drivers do not have meaningful names at all. They are all meaningless names prefixed with sub. We recover function names by leveraging several facts. The first fact is that most classes in driver inherit from classes in the kernel, and these kernel classes have symbols. The second fact is that in C++, when a child class inherits a parent class and overrides a virtual function, the parent's function and the child's function should have the same name and the same offset as shown in this figure. So with the above facts, we can recover the names of virtual functions that override functions in kernel classes. Actually, this is not a complete solution, but it can cover plenty of critical functions. Another critical feature of Ryuk is that it can resolve types of local global and member variables in the decompiled code. Its method is to first identify local variables types and then perform type propagation along control flows. There are mainly two kinds of local variables, which are called parameter variable and stack variable. For parameter variable, we identify their types by leveraging a fact that is, in the binary, C++ function names are encoded with the function's class name and the parameter types. So, by encoding these names, we can know the function's parameter types, just as the figure shows. For stack variables, we identify their creation and initialization by finding some typical functions as listed here. So after variable types are identified, we can propagate its type along function's control flow graph. During type propagation, we figure out what variables are assigned with the variable whose type is defined. And then send the types for them according to the identified type, just like this figure shows. Next, we extend cross-reference for member variables and virtual functions. We examine every sentence in the decompiled code of all functions and check whether any member variable or virtual function is used. And then we add a cross-reference in the editpro from the usage of from this usage to member variable or virtual functions location in their class or vtable structures. And then now you can see that the compiled code now looks more like the source code, right? Further, in order for better reverse engineering experience, we extend US operations in editpro. For example, as the demo will show, Ryuk allows jumping to a virtual functions implementation by just double click on a virtual functions call. You can see that when double click, we can directly jump to the functions implementation, and we can also jump to the child's into implementation by pressing a hotkey. Okay. Finally, after variable types are identified, virtual function calls are resolved, and now we can generate call graphs for all drivers. And this call graph is very important for further inter-procedure control flow and data flow analysis. And now everything is ready. We can do manual analysis or other kinds of static analysis as we want. Below, we will show a use case of Ryuk, which is called Ryuk fuzz. The idea of Ryuk fuzz is to guide driver fuzzing with static analysis results. We implement it by integrating Ryuk with the state-of-art driver fuzzer, passive fuzz framework OS 10. Ryuk fuzz takes two steps. In the first step, it performs data flow analysis to infer drivers required user input formats. And the second step uses the inferred input format to get input generation in the fuzzing process and improve fuzzing efficiency. So in its first step, we perform static data flow analysis in the decompiled code to identify whether user input is checked in conditions and what parts are checked and what is the condition. Just like this figure shows that we can identify that the offset 24 and size 1 should not be equal to 6 or 1 in order to avoid this failed pass. And then we can know drivers' requirements on user inputs for different execution paths, and use such knowledge to get fuzzing. But passive fuzz framework OS 10 only works on macOS 10.11 now. For later versions, there are several errors that need to be resolved. The first error is that it uses wrong buffer size to read the kernel header. Passive fuzz framework OS 10 suppose that the size of the kernel header is less than 1 page. But actually, after macOS 10.12, the kernel header is larger than 1 page. In order to solve this problem, we changed the buffer size to 2 pages. The second problem is that passive fuzz framework OS 10 uses a wrong way to infer the kernel text space. In its original implementation, it defines the address of interrupt handler, which was in the kernel text section, and uses this address to find the kernel text space. But for now, in the current macOS, the interrupt handler is no longer in the kernel text. As a result, we cannot find the kernel text space with the handler address. This change is caused by Apple's mitigation on the famous meltdown vulnerability. In order to defend against meltdown, Apple decides to move the interrupt handler and some other code related to the user space from the kernel text to another special location, just like the figure on the right suggests. So now the interrupt handler is not in the kernel text space. As a solution, we look for the kernel text space with another method. That is, we find the address of some other kernel functions. For example, the address of lock mutex lock, and traverse back to find the kernel text space. And this is more stable than the previous method. In conclusions, in this talk we have shown several vulnerabilities that can be exploited for privilege escalation on macOS, and we have introduced the technique of exploiting user-free vulnerabilities in the kernel, and we also explained a new static analysis tool called Ryuk, and also shows a use case called Ryuk fuzz. Most importantly, part of the Ryuk has been open sourced. You can fork Ryuk or start Ryuk on my GitHub. And also, very welcome to follow us on Twitter and Weibo. My Twitter account name is BXL1989, and Spark's Twitter account name is Bai and Zheng. That's all. Thank you for your attention.